After learning about radian measure, we hopefully start recognizing the significance and the importance of why radians is in fact most of the time better than degrees. We're so used to working with degrees from the time we're young, whether you think about a snowboarder jumping and doing a 360 or a wall, two walls meeting at a 90-degree angle. But now when we start to see applications involving trigonometry, involving circles and arc lengths, and how long the outside of a circle is, or how far a gear has turned, or whatever it might be, we have to be in terms of radians in order to accomplish these applications. So I'd like to start off by looking at the relationship between angles inside of a circle and the amount of distance traveled along the outside of the circle. When we look back to the diagram and the purpose of a radian, or what the significance of a radian is, remember that if we have a radius of r, then 1 radian is considered the angle that's formed when I wrap the radius around the outside of the circle. So I know that 1 radius, traveling 1 radius around the circle, gives me an angle measurement of 1 radian. Well, let's say we wanted to take a look at a different angle other than 1 radian. We should now notice that this angle, somewhere else in this rotation, also correlates to some arc length between the endpoints of the angle. We refer to all arc lengths along the circle as S. What S represents is the distance around the circle. So now what we should recognize is that all the lengths of the arcs are proportional to the measures of their interior angles. So we could set up a proportion here that demonstrates that the relationship between S and theta will always be equal to the relationship between R and 1 radian. So I know that the arc length then can be found by simply multiplying this across and finding out that by multiplying by theta, the arc length is equal to the radius times the angle. But it's really important to recognize that that angle must be in radians, because the radian measure is actually describing a real number, the units of distance that are actually traveling around the outside of the circle. So to demonstrate what I mentioned in the radians lesson, I want to demonstrate why theta is in fact unitless. And I'll just give an example here. So let's just say that we have the radius of a circle is equal to 3 inches. And let's say that the arc length around the outside of the circle is 8 inches. Okay. We'd like to find the angle. So let's take a look at this in terms of a diagram. When we look at a circle with a radius of 3 inches, if I wanted to wrap around by 8 inches, that would mean that I'd first of all have to travel 1 radius, which would take me about to there. I would travel a second radius, which would take me about to here. And not quite, that would be 3 inches, 6 inches, and we need to go a little bit more, so perhaps approximately right here. So that would mean that this whole distance on the outside is 8 inches. So now we have a method to be able to find out what the interior angle is, which we refer to as theta. Okay. And so notice that in order to find theta, we could just use the formula that S is equal to R theta. But by dividing by R, we could also represent theta as the arc length divided by the radius. And notice what happens when I divide the arc length, which is 8 inches, by the radius, which is 3 inches. those inches cancel, and all I'm left with is 8/3 for my angle. There are no units for theta now. So we should recognize that the reason we say theta is unitless is because of the fact that the arc length and the radius are the same units. And when those units cancel, this theta simply gives me the number of radii that I had to travel through in order to get to 8 inches. So that means that this is approximately 2 2/3 or approximately 2.67 radians. So I had to travel more than 2 radii, but less than 3 radii, and that's why my angle is 8/3. And based on this arc length formula, we're going to also be able to use this information to find arc lengths as well. Now, a great example of arc length is the distance around the outside of the Earth at different locations. So latitude and longitude are ways for us to measure angles from the core of the Earth to various locations on the Earth. So latitude is simply the measure of the angle with the vertex at the center of the Earth over here, with the vertex over at the core of the Earth. Okay. And the initial side is always at the equator. So we just think about if the equator was wrapping around, this is how we measure the latitude. So the North Pole would be at 90 degrees latitude because its rotation up to the North Pole is 90 degrees. So now we're actually told just a couple of locations on the Earth. Reno, Nevada is approximately due north of Los Angeles. And the latitude of Reno is 40 degrees. So as we can see in the diagram, that Los Angeles is closer to the equator than Reno. But Los Angeles only has a 34-degree latitude, while Reno has a 40-degree latitude. So now we see that there's 6 degrees in between. With this 6-degree angle, you can see that we really have this sector. This is referred to as a sector of a circle, a piece, kind of a pie wedge of a circle. And what we're trying to do is find that arc length, which is the distance from Los Angeles to Reno. So in order to do so, we need a formula. We need to use the fact that S, the arc length, is equal to the radius times the angle. Now the radius is the radius of the Earth. So the arc length is going to be the radius, which is 6,400 kilometers, times our angle. Now notice that our angle is 6 degrees. But you got to realize that operations with degrees don't work the same way as operations with real numbers. So I can't just multiply 6,400 times 6 degrees in order to find the arc length, because this must be in radians. So the first thing we need to do is we need to convert theta into radians. So remember, if I have 6 degrees, I can multiply by that conversion factor. That would cancel degrees and turn into radians. So we're going to multiply by 180 degrees, which is going to cancel the degrees. So I put that in the denominator. And pi radians goes up top. Pi radians and 180 degrees are the same location. So anytime we divide both of those, we get a result of 1. And so I'm not changing anything by multiplying by that factor of 1. And so notice this gives us pi over 30. So that's it. So we can now plug in our radian measurement, so 6,400 times the radian measurement of pi over 30. But it doesn't make sense in an application to keep things in terms of pi. So I wouldn't say, 6,400 pi over 30 kilometers for this distance right up here. So instead, we're going to come up with a decimal approximation and multiply. Okay, so let's take pi divided by 30. Now, whenever possible, you should try to use the pi button instead of just 3.14. So when I divide that by 30, I can now multiply by 6,400 And therefore, my answer is 670. So S is approximately 670 kilometers. And so notice that in order to find any information regarding its arc length or an angle within some portion of rotation, the formula we're going to use all the time is S equals R theta. Now this one was relatively straightforward because we were given an angle, we were given the radius, and all we had to do was multiply to find the arc length. Sometimes we have to do a little bit more thinking to be able to solve. So here's another situation involving rotation, where we're asked something about, as one gear rotates, how does that affect the other gear rotating? So we first of all start off with this diagram here, where we see that one radius is 2.5 centimeters. Okay, we'll call that R1. And the second radius, or R2, is 4.8 centimeters. Okay, so it says the two gears are adjusted so that this gear turns, and it causes this gear here to turn. So if this one starts turning this way, and the teeth catch on, it's going to be turning this one this way. And so we're told that if the smaller gear rotates through 225 degrees, so let's think about where 225 degrees is. Remember from our unit circle, the 225 degrees is going to rotate, first of all, halfway, which is going to take me to 180. And 225 is 45 degrees into the third quadrant. So it's going to travel through 225 degrees. So that means that for the small gear, theta is 225 degrees. All right, well, if we're given a radius and we're given an angle, then we should be able to find what our arc length is going to be. Because if this here, the outside amount, this amount that it actually rotates, is going to transfer to a certain distance that this one will rotate. It's obviously not going to be 225 degrees because it's like a string being placed onto the other gear. So let's go ahead and find out, first of all, for our first gear, or for our small gear, let's find the arc length. So our arc length is going to be S equals 2.5 times 225 degrees. But again, this value must be radians. So if you think back to the 225 degree angle, it's a 45 degree reference angle in the third quadrant. So I know that that's going to be a multiple of pi over 4. Now I have to think about where that is. Well, if this back here is pi, or rather 4 pi over 4, then I've just gone an extra pi over 4 to mean that what's left is 5 pi over 4. So I know that my unit circle radian measurement for 225 degrees is 5 pi over 4. And we're going to keep this as is. We're going to try to simplify this a bit if we can. Okay, so first of all, let's find 2.5 times 5. That's 12.5. So this gives me S equals 12.5 pi over 4. And that's the number of centimeters that we've turned. So notice that that's how many, that's the green amount. That's how much on the small gear, how much we've actually turned. Okay. So we're going to take that amount now and recognize that for the large gear, we're being asked to find out through what angle, through how many degrees will the larger gear rotate. All right, so we should be using the same formula, S equals R theta, except now we have 12.5 pi over 4. And I'm avoiding finding a decimal representation of this because I want to try to find an exact value or round at the very end of the problem at the very least. So now we have 4.8 times theta. All right, well, if we divide both sides by 4.8, okay, then we just multiply the denominators of 4.8 times 4. That gives me 19.2. Okay, so what we really have here is 12.5 pi divided by 19.2, and that's the number of radians for theta. But notice, since this is the number of radians and I need to convert to degrees, I need to multiply by a conversion factor that's going to cancel the radians and turn into degrees. And the only reason I know I'm finding degrees is because that's what the problem asked for. It said, how many degrees will the larger gear rotate? Okay, so most of the time it's totally fine to leave it in terms of radians, and I might come up with a decimal for that. But at this point right here, we're going to multiply by the conversion factor of 180 degrees over pi. And now the pi cancels. So whatever this becomes in our calculator is going to be the final result. So let's multiply 12.5 times 180. Divide that by 19.2. And my answer is approximately 117.2 degrees. So what that shows is that if this turns through, if this small gear turns through 225 degrees, then by the time it touches here, that's going to turn through 90 degrees and a bit more. Okay, 27 degrees more. And so notice that that's how far this one is going to actually turn. So just by using this arc length formula, we're able to actually find information relating to any rotation or any circular figure where we're asked something about the relationship between the angle that it rotated and its arc length. Now, one more application involving radian measure has to do with finding the area of a sector of a circle. Now, a sector, remember, is nothing more than just a pi wedge that's formed on a circle where the outer edge is an arc length. So this right here would be considered a sector. And we want to come up with a formula for being able to find the area of that sector. So before we can do that, let's go ahead and take a look at finding the area of a full circle. Okay. Now, if I was to look at the area of the entire circle, you should remember that, again, that the area, okay, the area for a full circle is pi times the radius squared. Pi times the radius squared. But I'd like you to show a couple of things here about the angle of rotation as well. So in order to think about the angle of rotation, we're going to look at this diagram a little bit differently. And we're going to think about this kind of like a windshield wiper. As I start to rotate around, I'm accumulating more and more and more area. Okay, so all of this area starts accumulating as I start moving my way around until I finally get all the way around to the full angle. Now that angle in this particular problem is 2 pi. And so the angle for theta is 2 pi. All right, so since theta is 2 pi, it looks like I'm multiplying by pi r squared, or I'm multiplying pi times the square of the radius, okay? Now I'd like to investigate how to find the area of just half of a circle. So notice that for half of a circle, we're rotating around so that the angle is just pi. And so for half of a turn, theta is equal to pi. And so now for the area of the portion of the circle, that area is now going to be half of pi r squared. Or if we want to combine the half with the pi, we could rewrite it as pi over 2 r squared. let's go ahead and do another example. Let's say that we only wanted to find the area of 1/4 of our circle. Well, the area of 1/4 of our circle is just going to be 1/4 of whatever pi r squared is. Or in other words, pi over 4r squared. But if you take a look now at the angle of rotation for here, this is just theta equals pi over 2, because 90 degrees is equivalent to half of pi. So now I'd like to take a look at a couple of things here. I'd like you to realize that the angle of rotation was 2 pi, but I'm multiplying r squared by pi. If the angle of rotation was pi, I'm multiplying r squared by pi over 2. If the angle of rotation was pi over 2, I'm multiplying r squared by pi over 4. You should realize that every one of the coefficients for area is half the size of the rotated angle. And so in general, the area of a sector is going to be r squared multiplied by half of the angle of rotation. So we now have a formula for finding the area of some sector. It's just half of the angle times the radius squared. So let's take a look at an example. Some of the original automobiles, there was a Ford Model A that was built during this time span, 1928 to 1931. And at the time, there was only a single windshield wiper, primarily for the driver, because that's the only one that needed to have the windshield cleared. And so the total arm and blade was 10 inches long. But the way that we know windshield wipers are, there's always this little gap at the beginning to where it's connected, to where the blade of the windshield wiper only starts a little bit further in. And so at this point right here, it says that it's rotated, that this blade rotates back and forth through an angle of 95 degrees. So the shaded region, more specifically, the region down below this line right here, is the area that's wiped clean. And what this is asking for is to find the area of the region clean to the nearest 10. So obviously that's a sector of some circle, because as it starts to rotate around, it's forming the outer edge of a circle. And so because this is an area, because this is a sector, we can use the formula that the area is equal to 1/2 theta times the radius squared. Okay, but that would be if we were to find the entire sector. What we really need to do is find the difference between two sectors, because we're going to have to subtract off this little piece right here. So why don't we start off by finding the area of the longer one, okay, which is going to be 1/2 for the, I guess we could say the area of the large segment is going to be 1/2 times 95 degrees times 10 squared. But then we also have the area of the small sector that we're going to have to deal with as well. So the area of the small sector is going to be, well, the difference here. If all of this piece is 7 inches, then I know the radius of this piece is 3 inches. So we're going to have to subtract off that piece in order to take out that sector. But it's still the same angle. So it's still going to be 1/2 times 95 degrees. Only now it's going to be 3 squared. But keep in mind, in order to do this, we can't use degree measurement, because products of degrees with real numbers doesn't really make sense. So again, we're going to have to go through the process of converting this into a radian measurement. So theta is equal to 95 degrees times, and again, I want to cancel out the 180 degrees here. Okay, and I multiply by pi. So if I cancel out a 5 from both the numerator and denominator, that gives me 19 pi over 36. So with that, then we can now find the area by simply taking the area of the large segment and subtract the area of the small segment. Okay, so that gives me, well, 1/2 times 100 is 50. So why don't we just say that this is going to be 50 times 19 pi over 36. And we're going to subtract the small area. So 1/2 times 9, 1/2 times 9 over here is simply 9 over 2. So that gives us 9 over 2 times, and we're also going to multiply by 19 pi over 36. All right. Okay, well, at this point, we could go ahead and just simplify a little bit and solve by finding a couple of decimal representations. So we could see that the entire large sector, right, starting at the center and rotating around, is going to be 82.9 square inches. But I need to take away this white region right up here in order to only get the orange shaded region. And so we have to subtract off 7.5. And when we do so, that just simply becomes 75.4. Now, always keep in mind, in application problems, we need units. Since this is an area and the length was in terms of inches, we know that this is going to be square inches. And there's our result. So with radian measure, we could see that we could find arc lengths, we could find areas of these sectors of a circle. Okay, anything relating to this circle in terms of lengths and radii and areas, we could find, as long as we convert the degree measurement, which is no longer allowed in application problems, as long as we convert it to the real number of radians.